So now we're finally to the modeling. So I'm going to call this M1, it's going to be model 1, and I'm going to write AOV because it's going to be an analysis of variance. And I'm going to use the AOV function to run an ANOVA of log sleep on VOR. So I've done that now, and I'm going to look at the summary of that output. So what do I get? I've got my usual ANOVA table. The predictor is VOR. Here's the residual error. I have the degrees of freedom for each of those. I have the sums of squares associated with each of those. By default, R does not also include the totals row, but of course the sum of squared total is the sum of these two. I've got the mean squared. The F is equal to the ratio of the mean squared, and there's a p-value. So this p-value is testing the null hypothesis that the mean log sleep is the same for each VOR group. And what we see here is p-value of 0.14. In other words, this data is not particularly shocking if the truth is that actually all five groups, have the same mean log sleep. I'm going to make a plot of residuals versus fitted values because what this ANOVA does is it calculates the mean in each of these 5 groups and then calculates the residuals from the separate means model in order to compare them to the residuals from the equal means model. In other words, for example, this data point, the residual is how far this animal's log number of hours of sleep is from the mean for all omnivores. So I have residuals and fitted values, and I can make a plot of them, right? Just showing you that I can do that with the ANOVA, residuals and fitted values. And I can add a horizontal line to that if I was interested in checking whether the values were equally likely to be above or below the line, right? Again, we can see that I can just spit out these fitted values. If you just look at these, you can see that these values here, 2.22, 2.36, 2.07, they're chosen from this set of numbers up here. Here's the 2.22, right? The 2.078. Because the predictions that we're making for each of these animals, the fitted values are just equal to the means from their group. Again, if an animal is an herbivore, the fitted value for that animal is the mean of the log sleep for all the other herbivores, including that one. What I'm going to do here is just make a little data set to show you a bunch of columns together. The VOR column, the log sleep column, the fitted values, and the residuals from this ANOVA so that we can look at them all together. Scrolling up to the top of this table, so you can see, for example, here's an animal that was a carnivore. Its actual log number of hours of sleep was 2.493. The fitted value was 2.22 because that's the fitted value for all the carnivores, and the difference between these two is the residual. Right, so 2.49 minus 2.22 is 0.27. The residual is exactly log sleep minus fitted value by definition. So that's what these are. The fitted values are just the mean within each group. The residuals by definition are the actual outcomes minus the fitted values. I'm going to display the output from the ANOVA again. And I want to show you that we can directly use these residuals in order to recreate the values in this ANOVA table. So for example, if I take the vector of residuals and square each value in that vector and then add them all up, that's the sum of squares residuals, right? So I can do that. I have a .1 here just to remind us that this is the first model we're looking at. If I do that, I get 20.864, and indeed that's the same number that I have as my sum of squared residuals. So the output of this ANOVA is not magic. This is literally the sum of the square residuals. I can also get the sum of squared total. So if this were an equal means model where I was ignoring VOR, I could take log sleep minus the mean of log sleep for everybody. So this is each person's log sleep minus the overall average. I can square those and then add them all up, and if I do that, I'm going to have a sum of squared total. By definition, the sum of squared due to the model is sum of squared total minus sum of squared residuals. So if I do that and print it out, now I'm back to my 1.894, and there it is, 1.894. So you can confirm the results in this ANOVA table just based on the data itself. There's nothing mysterious here. Each of the mean squares comes from sum of squared divided by degrees of freedom, etc. So that's the ANOVA. We ran an ANOVA of the continuous outcome on this categorical variable. But what happens if I instead specify a regression model that looks at log sleep by this categorical variable, by VOR? So I'll make a plot where the x-axis is going to be VOR and the y-axis is going to be log sleep. Note that when I do that, I just get back to the same box plot because when the variable you put in the x-axis is categorical or a factor, R will just draw you a box plot instead of a scatter plot because you can't make a scatter plot with an axis that's not numeric. Now I'm going to run the regression, so it's going to be M1 because it's the same model, but .lm because I'm running it as an LM, as a linear model of log sleep on VOR. Okay. When I summarize this, the output is going to look different than the output of the ANOVA, even though it's the same model, because by default the regression presents different numbers as part of a summary of the model fit. Let's go look at this. So what's in here? The first thing that comes out of the regression output is just a repeat of what you put in case you forgot. So that's helpful. The next thing is the summary of the residuals. So let me skip down to this. I have in the code down here, actually for the ANOVA, but it works for the LM as well. Here, I'll add it. Why don't I add it right where we are? So if I look at the residuals and I summarize the residuals, you can see that this output right here matches exactly what comes out. It's different rounding, but what comes out of the summary of the regression itself. So that's just literally a summary of the residuals. Then I have my table of coefficients. Here are my estimated coefficients, their standard errors. The t-values by definition are the estimates divided by the standard errors, and then a p-value for each of those. What are these p-values showing? Well, as in any multiple regression, each p-value is comparing the actual model I ran to what that model would be like without just one row. So for example, this 0.807 says that under the null hypothesis that you don't need the indicator for VOR being missing, this data would not be surprising, right? So this model that we have here with indicators for herbivore, indicator for insectivore, indicator for omnivore, indicator for missing VOR, is not any better than a model that just has the first three. That's what this 0.807 means, that this term the data doesn't contradict the assumption that we don't need that particular row. Okay, so we have those. We can again make fitted value and residual plots, residuals versus fitted value. So I'm going to make that plot. And although you may not recall, that is exactly the same plot we saw before. And if you're following along by downloading the code, you can check that. That's exactly the same. But let's start to check it. So here I'm going to put together in a matrix the fitted values from the ANOVA and the fitted values from the linear model. And what you can see is that for each row, those are exactly the same number, because what each of these models is doing is fitting the mean within a group as the predicted value, as the fitted value. So if you are a carnivore, then regardless of whether I call it an ANOVA or a regression, the mean for somebody like you is the mean in your group, in your VOR group. Similarly, I could do cbind to make a similar matrix showing you the residuals from the ANOVA and the residuals from the regression, but that would be boring because it's exactly the same idea that I just showed. Instead, I'm going to show you there's a function in R called identical, and I can ask if these two vectors are identical, and lo and behold, they are. In other words, both the ANOVA specification and the linear model specification are just splitting the sleep totals into groups based on VOR, and the predicted values are exactly the mean in each of the VOR groups. And the residuals are just the actual log sleeps minus the fitted values of log sleeps. Similarly, I can get the coefficients out of either of these models. Even though the ANOVA didn't show me the estimates of the betas, the coefficients, and the linear model output did, right? So this says that my model is 2.22 minus 0.14 times herbivore plus 0.41 times insectivore, etc. These estimates didn't come out as part of the ANOVA output by default. But if I either type m1.lm and then give me the coefficients, right? If I do that, this is the linear model output, it gives me just the vector of these coefficients. I could do the same thing with m1.aov since it's the same model, right? And that's exactly the same vector of coefficients. So even though the ANOVA didn't explicitly, as part of its default output, give me the coefficient estimates, that's part of what's going on. That's the same set of coefficients that are used. Now let's try to understand that better. I'm going to again look at log sleep by VOR. So the carnivores are the default, the omitted value here. In other words, of this categorical variable that has 5 levels, the 4 levels that are listed as indicators in the model are all of them except for carnivore. R by default will always choose the one that's first in alphabetical order as the baseline. Okay, that's why the intercept is 2.22. It's equal to the mean for the carnivores. If you're not an herbivore and you're not an insectivore and you're not an omnivore and your vor is not missing, then you must be a carnivore. All these terms will be equal to 0 and you'll be left with the intercept, which is 2.22. However, if you're an herbivore, then you should have a 1 for your herbivore indicator and 0 for all the other indicators. And so our estimate of your log sleep should be 2.22 minus 1 times this quantity. In other words, it should be equal to 2.08. So this specification, these set of coefficients, is just another way to say that we're going to use as your predicted value whatever the mean is in your own group. And that's true regardless of whether we call this via ANOVA or via a regression.